The universally accepted protocol for maximizing lean muscle mass is highly specific: 6 to 12 repetitions, 60 to 90 seconds of rest, and a slow, controlled lowering of the weight on every rep. While a powerlifter moving their absolute maximum physical limit develops profound neurological strength, a bodybuilder utilizing submaximal loads within this rep range develops significantly more total muscle mass. If mechanical tension is the primary driver of adaptation, lifting lighter weights should theoretically be less effective. Skeletal muscle growth is a multi-pathway response. It requires a triad of overlapping biological stressors to reach its maximum physical potential. That triad consists of mechanical tension, muscle damage, and metabolic stress. The standard gym protocol functions as a balanced biological algorithm designed specifically to trigger this exact triad. This algorithm exists to bypass a specific biological constraint. Skeletal muscle is a post-mitotic tissue, meaning the cells do not divide or replace themselves throughout life. Every fiber is bound by the myonuclear domain constraint. A single nucleus can only regulate protein synthesis for a strictly finite volume of cellular space. To increase a fiber size past this limit, the cell must acquire new external nuclei. These new nuclei come from dormant myogenic stem cells called satellite cells, located just outside the fiber membrane. A mechanical stimulus forces these cells to wake up, proliferate, and physically merge with the existing fiber, depositing their nuclei to expand capacity. Creating an environment that forces satellite cell fusion is the only way to achieve significant growth. Analyzing the first variable, intensity, explains why the 6 to 12 repetition range is mathematically superior to the 1 to 5 range. Sets of 1 to 5 reps maximize mechanical tension and AKT-mTOR signaling, but they rely almost entirely on the short-lived phosphocreatine energy system. Extending the set to between 6 and 12 repetitions exhausts the phosphocreatine stores, forcing the muscle to rely on anaerobic glycolysis to sustain ATP production. This chart shows metabolic accumulation across repetition ranges. The 1 to 5 rep range remains flat, while the 6 to 12 rep range shows an exponential spike in lactate and hydrogen ions. This acidic, hypoxic environment triggers a massive systemic release of growth hormone. These hormones act as the upstream regulators that signal satellite cells to begin their proliferation phase. Metabolic stress, experienced as a local burning sensation, functions as a primary, mandatory anabolic signaling mechanism. The second variable, the 60 to 90-second rest interval, manipulates vascular dynamics. 3 minutes allows full strength recovery, but entirely dissipates the metabolic stress. 30 seconds of rest maintains stress, but destroys force output for tension. A 60 to 90-second window creates a vascular trap. Exiting veins remain compressed by residual muscle tone, but arteries continue pumping blood into the tissue. Fast-twitch fibers utilize high concentrations of aquaporin-4 transport channels to rapidly draw this trapped blood plasma directly into the cell. This extreme hydration physically stretches the cell membrane from the inside out. The cell perceives this swelling-induced membrane stress as a threat to its structural integrity. It responds by synthesizing new proteins and reinforcing its ultrastructure. The third variable is repetition speed, specifically the requirement to lower the weight slowly under load during the eccentric phase. Eccentric actions cause a biomechanical reversal of the size principle. Fewer motor units are active, forcing a smaller number of fast-twitch fibers to absorb massive tension. This concentrated load results in non-uniform lengthening that shears the myofibrils, leading to structural tearing known as Z-line streaming. The body initiates an inflammatory response to this myotrauma, sending neutrophils and macrophages to clear the cellular debris from the torn Z-lines. These macrophages release specific cytokines like IL-6, which act as a chemical homing beacon, directing proliferated satellite cells exactly to the site of the damage. Eccentric microtrauma functions as the biological targeting system that ensures new myonuclei are donated to the precise fibers that need to grow. The final variable, multiplanar volume, is required because of the specific architecture of human muscle. A muscle does not fire uniformly. History's most successful physiques were built using an incredibly wide variety of angles and implements. This is due to compartmentalized innervation. Distinct regions and architectural bands within a single muscle are wired to entirely separate nerve branches. Because of this wiring, a fiber in one compartment can be completely exhausted, while an adjacent fiber remains dormant, depending on the angle of leverage. To maximize total cross-sectional area, a multi-angled mechanical attack is necessary to exhaust every isolated compartment. The standard 6 to 12 rep 90-second rest protocol operates as a precise mathematical intersection of biology. The heavy load activates the fast-twitch fibers, the 12 repetitions force anaerobic glycolysis, and the 90-second rest creates the osmotic trap. This radar chart plots tension, metabolic stress, and muscle damage. The axes expand in perfect symmetry only under the 6 to 12 rep 90-second rest parameters. Conversely, a powerlifting profile spikes tension, but metabolic and damage axes collapse, drastically shrinking the overall hypertrophic stimulus. Cell swelling and eccentric damage are the mechanisms directing satellite cells to fuse and execute growth. Hypertrophy results from the deliberate, calculated engineering of a mechanico-chemical signaling cascade.